Okay, let's finish off module 10 and 11. We'd previously done. Oh, the question is, wait, this isn't 10? It's 10 and 11. So basically, you get these two are tied together. So we had done at least one example where we predicted a reaction based on the MOs, where we said, oh, if we take this SH minus, the lone pair on sulfur is the best donor, the sigma star CCl is the best acceptor, and we just followed that to its logical conclusion, and we said we'd make a new bond. So we're going to do two more examples where we predict a reaction. And that'll kind of close us out. So here, this is a reaction between methanol and alcohol, and then this thing that's a carbocation. So I'd like you to take a moment, draw MO diagrams for these. For the one on the right, I recognize there's 9 CH bonds. So if you're drawing the MO diagram, you can just, instead of drawing 9 little lines to represent 9 orbitals, you can just say 9 times and draw one line to represent that. Take a minute to draw MO diagrams for those two. All right, I drew in my orbitals up here. Help me fill in the labels. So let's start from the bottom on the one on the left. Sigma CO, sigma OH, sigma CH, oxygen lone pairs. All right. And then I should have electrons up through the lone pair. All right, just to double check, carbon should have 4 orbitals, oxygen should have 4 orbitals, and then there's 4 hydrogens, so that should be a total of 12 orbitals. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 orbitals. All right. For the one on the right, at the bottom I have sigma CC, and then sigma CH, and then sigma star CC, and sigma star CH. So I should have 4 orbitals from each carbon, so that should be 16 plus 9 for the hydrogens, so that would be 25. Right now I have 12 plus 12 is 24. What did I leave out? The positively charged carbon, remember, doesn't follow the octet rule. So what kind of orbital does it have? All right, it's a carbocation. It has an empty non-bonding orbital. So that's that trick orbital that I said will show up from time to time. So anytime you have a carbocation, remember that vacant orbital is there. So if we had to guess what our best donor and best acceptor in this case would be, what are they? Yeah, this is the lone pair on the oxygen is going to be the best donor. And then the vacant p orbital on the carbon is going to be the acceptor. So if I'm going to draw a curved arrow, where should my curved arrow start? at the oxygen. It's starting in a lone pair, so I'm going to draw in the lone pair before I draw my arrow. Where should my arrow end? Should end at the carbon. So now I'm forming a new bond between which two atoms? Oxygen and carbon. I had a positive formal charge before. Where is it now? It can't be neutral. I can't have just destroyed the positive charge. Now the positive formal charge is on oxygen. One thing that sets this apart from a lot of the other examples we've seen, since the acceptor was non-bonding rather than anti-bonding. No bond needs to get broken, yeah. So all we did was form a bond. All right, we just predicted a reaction. Questions about that example? All right, let's do one more. All right, so again, I filled in the lines, helped me put in the labels. Starting from the bottom over here, what's my lowest energy orbital? Sigma CC, Sigma CH, Pi CC, Pi star CC, all right, now I would fill in electrons. Up through the pi, and then over here for HBr, I've got sigma, oh, there's no C, sigma HBr, I've got sigma star HBr at the top, and in the middle I've got the bromine lone pairs. All right, so now I have to decide who's going to be the donor, who's going to be the acceptor. And there's not necessarily a clear winner. I could start by just identifying the HOMO and the LUMO for each. So for the molecule on the left, what's the highest occupied molecular orbital? Pi CC. What's the LUMO? Oh, on this one. Pi star CC is the LUMO. For the one on the right, the bromine lone pairs are the HOMO, and sigma star HBr is the LUMO. So you might be inclined to say, well, lone pairs are usually better donors than pi bonds, and pi star should usually be lower than sigma star. So you might be inclined to make the bromine lone pairs donate to pi star CC. This would be totally a reasonable interaction to consider. Or you could consider the other option where I have pi CC donate to sigma star HBr. And this is an example where I think you need a little more information to be able to make the choice. I think the last case was pretty clear cut. It was pretty clear cut that when you have a neutral molecule and a positive molecule, you're probably going to donate to the positive molecule. When you have a negative ion, like we did in this first example here, usually the negative ion is going to be the donor. Here we have two things that are neutral, and it's not necessarily clear which should be the donor and which should be the acceptor. This is where some of those hints that I gave you come in. And one of the hints that I gave you is that generally, pi star CC is not a great acceptor. And so we're going to go with we're going to go with the second interaction here, the one I outlined in purple, where pi CC donates to sigma star HBr. So if that's my donor, sorry I just gave it away, but if that's my donor, pi CC, where should my arrow start? At the pi bond. And where should my arrow end if I'm donating to sigma star HBr? Should end. Which atom are the electrons going to be more attracted to? The hydrogen or the bromine? Why? Bromine is more electronegative, so what's the polarity here? What's the partial charge on bromine? Bromine's partially negative, hydrogen is partially positive. So if you're a pair of electrons, who are you going to go to? To the positive. So generally we attack the less electronegative atoms. So that my arrow is going to end at hydrogen. If I think about what sigma star HBr looks like, it's going to have a big lobe on hydrogen and then a small lobe on bromine. So we're going to attack the hydrogen. Since I'm donating electrons into an antibonding orbital, what's going to happen to the HBr bond? It'll break. Now, when a pi bond attacks something, we're left in a bit of a quandary, because what this means is we're forming a new bond to the hydrogen, but from what atom? Well, in this case, it's going to be from one of the two carbon atoms. They're equivalent, so it doesn't really matter which one I choose. But I'm going to form a new bond from one of the carbon atoms to the hydrogen. And I'm going to break the bromine off. Bromine had 3 lone pairs before, now it has 4. So what's missing from my drawing? Formal charge. Bromine is now negative. The carbon on the left over here that didn't get the bond ends up positive, yeah. So, in this case, when we have pi cc as a donor, it's going to make a new bond to one. We're going to make a new bond to one of those carbons. The other carbon is going to be left high and dry. And so then there'll probably be some following reaction step where that reacts. And part of what we would talk about in a future molecule, where we talk about reactions of alkenes, is all right. Which carbon should be left with the positive charge? Which carbon should we form the new bond to? In the example we just looked at, there was no difference; they were equivalent, so it didn't matter. And just to go back and fill this in, what I outlined in green is one option, but it turns out not to work as well. And we're just about out of time for today. That's basically Module 11. Yay! Thank you.